see in the previous program, from the program execution sequence, what we can see here is all the tasks they are executed in a fixed fashion, one after the another, and always whenever the program is being run, they get executed one after the other only. That is, first task getting executed first, then the second, so on so forth till the nth, and same thing will go on continuing. Here, what we can say here is the operation is being done in an infinite loop. Same thing, we can go for writing a code in the C language. See, we have the program in the C language here. In the initially the configurations are functions for the configurations are defined. Then you have the initializations being done. Then you have a continuous while loop. Continue while one means it's a continuous loop. In this loop, first thing is the task one. Function for the task one is getting executed. This gets followed by the functions for the task 2, so on so forth till the task n. Soon after the execution of the task n, again it is the loop will continue. That is, it will go back and go for executing the task 1 only. So it is in a continuous loop. We have a continuous loop, and the repetition is done using an infinite loop. The infinite loop that we are using here is while one loop. This approach we are also calling it as super loop based approach. Here tasks are running inside the loop, and the only way to come out of the loop is either by a hardware reset or by an interrupt insertion. In the hardware reset, the program execution will come back to the main loop. Whereas in an interrupt request, whenever an interrupt request happens, this request will go for suspending the task execution temporarily, and it will go for performing the corresponding interrupt routine, and on the completion of the interrupt routine, again it will go for doing the task at what point it has left, or what you can say it will go for restarting the task execution from the point where it had got interrupted. So there are two ways in order to coming out of the loop. One is the hardware reset, and the other one is interrupt assertion. Hardware reset, what it will do? It will go for bringing the program execution back to the main loop. With interrupt, what is happening? Wherever at what task the interrupt is getting interrupt is acknowledged, from that point the program will go for running the interrupt service routine. Once the interrupt service routine is done, on the completion of the interrupt service routine, it will start at the point where it had left the execution. The super loop based design, it doesn't require an operating system, because there is no need for scheduling. With scheduling only, we are going to say which task has to be get executed after which. Here already we have the priority set. First task gets executed first, then the second one, so on so forth till the nth. So there is no need for checking which task has to be executed first. So there is no need for scheduling. And in the super loop approach, even the priorities are fixed. We are going to put the task with respect to their priorities. For highest priority task will be the task 1, least priority task will be the task n. So the priorities also are fixed. And whatever code we have in order to perform these tasks, that will be stored in the code memory, and we don't have to have the operating system image there. Directly can go for storing the program which has got the predefined task in the code memory. And with respect to this, we can go for using a low cost embedded product. And these products, we don't have to have time critical functions to be done. Low cost embedded products, and in these products the response time need not be time critical. And some of the embedded products will go for demanding this type of approach. And the tasks are sequential. Can take the example of a card reader, electronic video game toy. In card reader, what is the job that has to be done? You'll go for inserting the card. Once you insert the card, what has to be happened here? The card authentication. Uh, After the card is authenticated, next thing is deleting the money. But reading the card with respect to only the device of reading card is card authentication. Authentication of the card will be done by checking whose card it is. And also in a video game toy, you have a keypad. You go for pressing the keys. The way you press the keys, your video display has to move. It has to take in and it has to move according to the key press. You have a predefined task here, and the tasks are not time critical. See, this super loop based design, it is simple and straightforward without any OS related overheads. Major drawback of this approach is if you have a failure in any part of a single task, this will definitely go for affecting the whole system. Failure in any part of a single task will affect the functioning of the whole system. The program will go for hanging up at some point while executing a task, it will go for remaining there for ever, and ultimately the product has to stop functioning. Program gets hanged up in some point while executing. So it will remain there only forever. As it remains there only forever, what will happen? The product has to stop functioning. We do have the remedial measures for overcoming this. We can go for using the hardware and software watchdog timers. Using the hardware and watchdog timers will help in coming out of from this loop when an unexpected failure occurs or when the processor hangs up. But for using this, you need to make use of the additional hardware and also firmware. Those are the overheads. Additional hardware and firmware are the overheads with respect to using of the watchdog timers. And one more major drawback with respect to the super loop is lack of real timeliness. See, here in this, if you have a large number of tasks to be executed in an application, if as the number of tasks goes on getting executed, the time at which each task is repeated is also increases. There will be long time, like if I am executing task 1 and if I have some 100 tasks, by the time all the 100 tasks are being done, again you come back to the task 1, the time gap is too much. So the time at which each task is getting executed, that also gets increased. So when this is happening here, there could be probability of some missing events. With respect, example here, what I can take is the keypads. In keypads, with respect to the super loop design, there will be a task for monitoring the keypad connected to the I/O lines, and this need not be the task running while you press the keys. That is, the key pressing event may not be in synchronization with the key press monitoring task within the firmware. So in order to identify the key press, again you'll have to press the keys for sufficiently long time till the keypad status monitoring task is executed internally by the firmware. This what has happened with this really will not have a real timeliness. What we can say here is it's a lack of real timeliness, and corrective measure for this is we can go for using a interrupt for external events. When you use an interrupt for external events, you can go for introducing the real time attention, because as soon as the interrupt comes, what the program has to do at whatever point it is getting executed, it will forego that, it will go for running the interrupt service routine. Once the interrupt service routine is done, again it will start from the point where it had left the execution. So for the external events, we can go for introducing the interrupts. By introducing the interrupts, we can go for achieving real-time attention. Apart from that, these days we have large advances in processor technology. And due to this, we have got the processors and the controllers at very low cost and also at high speed. We can go for using such processors in a super loop design, so that it will go for reducing the time required to service different tasks, and thereby it can go for providing a real time attention to the external events. So one thing is, for the external events we can go for using the interrupts, or we can go for using the low cost but high speed microprocessors or controllers for the super loop. Second one is embedded operating system based approach. So in this we are going to have the operating system. It's a operating system based approach. So when we have the operating system, we can go for having either a general purpose operating system or a real time operating system. And this will go for hosting the program that is written by the user. Program that is written by the user will be stored with respect to these systems, either in a general purpose operating system or in a real time operating system. Coming to the general purpose operating system. General purpose operating system, here the design is very similar to the conventional PC based application development. That is the way you write your program for your PCs. And there you have the operating system in your PC. The operating system can be Windows, it can be Unix, it can be Linux, anything that you use for your desktop PCs. And you'll be creating and running the user application on the in that only. You'll be creating and also you'll be running the user application in that. The operating system may vary here. Example of a general purpose operating system in the embedded product development is Microsoft Windows XP Embedded. Coming to the RTOS based design. In the real-time operating system based design, the embedded products, they go for demanding a real-time response. They need a real-time response. So in RTOS, response has to be done in a timely and predictable manner with respect to the events that are being run. It has to be very much timely and it has to occur in a predictable manner with respect to the events. The real-time operating system, it will go for containing a real-time kernel. This real-time kernel is responsible for performing preemptive multitasking, schedule for, it has got the scheduler for scheduling the task. It will go for running the multiple threads, all the jobs that are needed in order for the timely operation in a predictable manner. Those will be there in the real-time operating system. With respect to real-time operating system, we can go for having a flexible scheduling. Flexible scheduling of the resources like CPU and memory. And it will offer some way in order to communicate between the task. Tasks are to be communicated from, if you are switching over from one task to another task, communication has to be established. So everything will be taken care by the real-time operating system. How the resources are being utilized, how the communication between the task is being run, everything will be taken care, and that will again depend upon the user input. Depending on how the user wants it to be run, user input, accordingly the scheduling and task switching will take place.